In this video, let's try to derive the PDF for the maximum of a sample. And so just some notation, we'll let x1 through xn be an IID sample, so independent and identically distributed, from some distribution. So I'm saying it's some distribution with a PDF f of x. And it'll also have a CDF capital f of x. And our goal here is to find the distribution. So find the distribution of the maximum of the sample. All right, so the goal here will be to start with the CDF of the maximum. And we know what that is by definition. It's the probability that the maximum value is less than or equal to some value little x. And so I think it might be helpful to draw a picture. And a picture might look something like this. We've got some sample values maybe that we've drawn. Right? All of those are values of the sample. They're something like an xi. And then we've got some particular x value. And what this probability statement here says is that the maximum value is less than or equal to little x. So that means that, in this illustration here, this is the max value, and it's less than little x. And so that tells us really that if the maximum value is less than little x, then every other value is less than little x. So this should be equivalent to saying that x1 is less than or equal to little x, and x2 is less than or equal to little x, and so on, up through xn is less than or equal to little x. And you might be thinking here that we just made things more complicated because we started out with a marginal distribution, right, the distribution of the max, and we ended up with something that's a multivariate distribution, right? It's got many components to it. It's a CDF in many dimensions. And in fact, that actually makes things a lot better once we take advantage of the properties of independence and identically distributed random variables. Because we don't know the distribution of the max, that's what we're trying to find. But we do know the distribution of each one of these sample points, right? Each one of these xi's. And the fact that we have independence, so the I here, the fact that we have independence means that we can actually multiply the marginal distributions together. So we have x1 is less than or equal to x. Sorry, the probability that x1 is less than or equal to x times the probability that x2 is less than or equal to x. Keep multiplying all the way up through the probability that xn is less than or equal to x. So we've used independence there. And then we can also use the fact that we have identically distributed random variables to say that, well, this is really just the probability that, say, x1, or just one of the random variables, is less than or equal to x, and just raise that to the nth power. And so there we were using the ID part of the IID. So we're noticing that we have identically distributed random variables, so we can take one of the CDFs and raise it to the n. Now, of course, we're noticing here that we have the CDF of x1 raised to the n. And that's the CDF of the max. And so if we wanted to find the PDF of the max, we'll call it little f of x parentheses n. and that will be equal to the derivative of the CDF. And so we've got to use a chain rule here, so it'll be n times the CDF of x raised to the n minus 1, and then the derivative of what's inside. Well, the derivative of the CDF is the PDF. So that should be the formula for you to find the distribution, so the PDF, of the max of a sample.